Okay, students, please grab a seat. Can folks in the back hear okay? Okay, one person can. I guess that'll do. Ah, two. Okay, I'll take it. This is lecture number 24, Announcements. Homework 7 will be published very soon. It's due next Wednesday. Immediately after that, there will be a quiz. Quiz number 3 will be released next Tuesday and due on Thursday. Just like previous quizzes, this one you have to do on your own. So it's open note, open interpreter, closed classmates, closed internet. In the meantime, while you're working all this stuff, you have an opportunity to earn back any composition points that you lost on projects 1, 2, and 3. All you have to do is make the changes that were suggested to you by the TA or tutor who reviewed your project in the first place, and then resubmit. So go make changes to your projects. That means you have to face your old code, a programmer's worst nightmare. But it's actually a wonderful way to learn how to improve your programming, to go back and read what you wrote, get someone else's perspective on it, and then make revisions based on that. This happens all the time. Every line of code that I wrote while I was at Google was reviewed by one of my coworkers, and they often told me to change things. So I know what you're going through, and I think it's good. When you're done, all you have to do is run Python 3 OK -- submit again. This is currently enabled for projects 1 and 2. Project 3 scores have not all been assigned yet, but they will be in the next couple of days, and then you can do that for project 3 as well. Questions? Okay, we want you to earn back all the points you lost on composition, so please do this. Midterm 2 scores went out on Sunday. The exam was hard. I think you know that already. You actually did great. I don't know if you know that, but congratulations on excellent work on a very challenging exam. It's a good idea to go back and review the questions. This is a good learning experience. If you have questions about why the solution is the way that it is, bring it into your TA or me, and we'll be happy to talk it over with you. If you think you were scored incorrectly, please let us know by filing a regrade request online. Those are due, I think, on Wednesday. I sent out a due date. All right, okay, let's go with Wednesday. And the goal here is that we can have all regrade requests processed and all of your other assignments evaluated before Friday, which is some administrative deadline, or whether you want to take the course pass or not pass. Okay, questions about that? Your score on midterm 2 is not final. You can get back some points already just by the old midterm recovery policy, which looked at whether or not you attended discussion section and turned in labs before the midterm. But I've also added an incentive to keep going to lab. You can earn back up to 5 points on midterm 2 by attending the 5 remaining labs this semester. This only applies to you if you scored 35 or below, but it's a good idea to get back these points. It's also a good idea to go to lab anyway. Lab is a wonderful place because it's filled with lab assistants and your TA, and they're all there to help you understand what's going on. And you can even ask questions about other stuff while you're in lab. You could ask about a homework assignment or a project or an old exam question. Get whatever help you need from the people who are there. Oh, so what about the 35-point threshold? Well, there's like some complicated function that I posted online where basically if you got 25 or below, you can get the full 5 points. If you got between 25 and 35, you can get some fraction of those 5 points. And above 35, you just get the score that you got. The reason I have these complicated functions is just to make sure that people who did well on the exam continue to have a high score in the course. So it's never better to miss an exam question and then get more points later. It's always better just to write the right answer the first time But if you don't write the right answer the first time, like if you had some trouble with midterm 2, you shouldn't give up. The course is not, your fate is not sealed. The course is not over. With these recovery policies, it should not be impossible for anybody to pass the course. You certainly can determine your fate by continuing to work hard, make sure that you master whatever material you haven't mastered yet, and show me on the final exam. The final exam is mostly about the stuff that we've already covered in the course. It's mostly about midterm 2 material. But it's worth more than midterm 2. So if you want a second shot at this stuff, that's what the final exam is for. Okay. You can complete the lab remotely, but you have to turn it in on time, and you have to get it right. So it's much easier just to go to lab, at which point your lab assistants will make sure that you finish it while you're in the lab session. Okay, so what's happened in this course so far? You've learned about functions and all the wonderful things you can do with higher order functions and recursion. You've learned about data and how you can represent hierarchical structures, how you can represent objects of all kinds. You basically know the Python programming language. There aren't that many details that we've left out. But in fact, you've learned how to program in any programming language, because they're more common than they are different. And so to prove that to you, today we're going to start learning an entirely new programming language called Scheme. Now, Scheme is important because people still use it. In fact, the community of people using it and languages like it is growing. Scheme is a dialect of a family of languages called Lisp. Now, why is it a family of languages? Well, there's a bunch of different languages that are almost the same. And they're all called Lisp of various sorts. And Lisp is the second oldest programming language that people still use. And it's by far the oldest one that people still want to use, that a growing community of people keeps using. And the reason why a growing people of community keeps using it is that it has beautiful properties, which we're going to learn in the next couple of weeks. Now, I said the next couple of weeks, but in fact, the language is so simple that we'll learn the whole thing today. Before I tell you about Lisp, I'll tell you about Lisp. What are people saying about Lisp? Alan Kay, who was in that video that you watched the Friday before spring break, invented the first object-oriented programming language. You would think he would say nice things about his own language, but no, he says Lisp is the greatest single programming language ever designed. Neil Stevens says the only computer language that is beautiful, and he's my favorite sci-fi author, so he must be important. Okay, so something wonderful is happening here. I'm going to teach you the whole language, and then we'll write some programs, and then in lab this week you can try it out. The homework is in Scheme, so you can try it out there, and the quiz next week will be in Scheme, so make sure you learn it by then, by learning it right now. Here are the fundamentals. In the programming language, all you write are expressions. No statements, only expressions. And those expressions can be primitive expressions like numbers, or the plus sign, or the word true, or the word quotient, or they can be combinations. This is the only piece of syntax in the language that you can put multiple different expressions in parentheses, and what this combination says is take the quotient of 10 and 2, which is 10 divided by 2, or 5. And this combination says take not of true, and not true is false. Every combination starts with an opening parenthesis and ends with a closing parenthesis. How do you evaluate an expression? Well, numbers are self-evaluating. Names are not called names in Scheme, they're called symbols. And the reason they're called symbols is that true and plus and quotient are all the same kind of thing. So they can be words or they can be actual symbols like plus. So all these things are called symbols. And symbols are bound to values in some environment. And so they evaluate to whatever value they're bound to. So when I say symbol in Scheme, that's like name in Python. But we're allowed to have names like just the plus sign. Now, combinations are call expressions. A call expression looks a little bit different in Scheme than it does in Python. It includes an operator and 0 more operands, just like a Python call expression, but the operator goes inside the parentheses instead of on the outside. So you write quotient 10, 2, and that gives you 5, instead of writing, floor div 10, 2 in parentheses. Whew. You know like half the language already. Any questions? You can nest one call expression inside of another. Oh, sorry, I'll read my speech bubble. Quotient is the name, the symbol for Scheme's built-in integer division procedure, which divides 10 divided by 2. Okay, I can nest one call expression within another. So plus 8, 7 is another call expression that adds 8 and 7 together to get 15. If I divide 15 by 5, I get 3. Question? No, Scheme will allow us to have as many arguments as we want. I'll show you an example in a minute. But first I want to show you a big nested example. Okay, so this says I want to add together what you get when you multiply together 3 and whatever you get when you add together the result of multiplying together 2 and 4 and adding together 3 and 5. Oh my gosh. Okay, so some notes on the thing that you see on the screen. New lines and indentation do not matter. All that matters is opening parentheses and closing parentheses. So all the indentation that you see here is ignored by the interpreter, but it can be useful for people to understand what's going on. So combinations can span multiple lines. The spacing doesn't matter. You can just make it up however you want. But a typical way to indent things is to put at the same level of indentation all of the different operands in the same call expression. So what we're adding together is the result of this product and this sum. And we're multiplying 3 here by whatever I get when I sum these two things together, etc. Someone just said the word tree. It is certainly the case that expressions are tree structured, and that we're fitting different parts within different parts. Okay, so I showed you how it worked on a slide. I'll start up Scheme. And in Scheme, as someone suggested, I can actually add together multiple different things all in one expression. 1 plus 2 plus 3 plus 4 is 10. What if I add nothing together? Nothing. I can multiply 1 and 2 and 3 and 4 and I get 24. I can multiply nothing together. What do you think I get? You get the multiplicative identity, which is what? Oh, they must have thought this through when they created this language. That's pretty clever. Subtraction's a little funny. If I have only one argument, then it negates it. If I have 2 arguments, then I subtract the second from the first. If I have 3 arguments, then I subtract both the second and the third from the first. And like I said, we can nest these things however I want. So I can multiply 2 by 2 by 2 by 2 by 2 by 3 by 3 by 3, and that'll give me some big number. If I want to subtract 1 from that, I don't put the minus in the middle. I put it at the beginning because it's a procedure. It's the procedure that subtracts one thing from another thing. And then I say, oh, I want to subtract 1 from this, and I'll get 863. And if I want to do some complicated mathematical procedure, then I have to put all the operators at the beginning, and then nest within them all of the operand expressions that I want to process. So if I want to divide and then add and then multiply, whatever, 7 and 4 and 3, then it's just going to do the math function. Okay, so there's built-in symbols like plus and times. There's also a bunch of built-in symbols that help you figure out what kind of value something is. So there's a type system in Scheme, just like there is in Python. I can ask, is this a number? And it'll say, yes, 2 is a number. What about true? Is that a number? No, that's a Boolean value. I can ask whether something's an integer. 2 is an integer, but 2.2 is not. I can ask whether something is 0. 3 is not 0, but 0 is 0. Now this question mark is not something special. This is all just part of a symbol. Number question mark is the symbol. Why is there a question mark at the end? Well, that's just a convention to say this is the kind of procedure that gives you back true or false. So it's just trying to indicate to the user what sort of procedure this is. Doesn't matter. So case matters in general, but not for true and true. Both of them work. There's also one of these. Okay, so why is it this? This is like an old Lisp convention from long ago that they decided that should mean true and that should mean false. You don't really need to know that. Okay. There's a little bit more to the language. Let's learn a little bit more. There's something called a special form. That's a combination, meaning stuff in parentheses, that's not a call expression. A combination that's not a call expression is a special form, and you kind of have to memorize all of these. But they are all supposed to be fairly familiar to you at this point. Here's one special form. It's called the if expression. You write the keyword if right after the opening parenthesis, and then you write down 3 expressions called the predicate, the consequent, and the alternative. And the reason it's special is that instead of evaluating all 3 of these and passing them in as arguments to a function if, instead it only evaluates the predicate, figures out if it's true or false, and then evaluates the consequent if it's true, and the alternative if it's false. So you can read this as if, the predicate, then the consequent, otherwise do the alternative. Way back in homework 1, we looked at examples of why this needs to be a special form. Because you don't always want to evaluate both the consequent and the alternative. If lets you pick one or the other. Okay, so there's an evaluation rule for every special form. This one says evaluate the predicate expression, then either evaluate the consequent or the alternative depending on whether the predicate's value was true or false. This is very similar to an if statement in Python with an else clause. There's also and or special forms. And is true if all of the expressions here evaluate to true, or is true if any of these evaluate. There's actually some special conditions that you'll read about in your project, so I won't go into them now, but I just thought I'd point them out as special forms. And then there's a really important special form. It might be my favorite. It's called define. Define gives a name to a value. So I could define pi as 3.14. And then I can use pi as a symbol in any other expression that I want. So I can multiply pi by 2, and I'll get 6.28, Now, what does it mean to define pi to be 3.14? Well, that means I'm creating a binding between the symbol pi and the value 3.14 in the current frame. Frames again. Yes. So, Scheme uses almost exactly the same model of evaluation that you see in Python, where you have multiple frames, a global frame, a local frame for each procedure call, and each one has a parent, and you look up the values of symbols just in the way that you would look up the values of names in Python. And actually, Scheme came first, and Python stole it from Scheme because it was a good idea. Okay, so how do we use these things in combination? Oh, sorry. I'm going to show you one more. Okay, so you can define a name for a number. You can also define a name for a new procedure. So a new procedure looks almost like defining just a symbol, but it has an extra set of parentheses. So what you say is you say define, and then within parentheses you say both the name of the procedure that you want to define and the name of the formal parameter of its argument. So this thing right after define should look just like a call. And this says if you take the absolute value of x, you evaluate that by evaluating this expression. If x is less than 0, then negate x. Otherwise, it's just x. So if x is greater than or equal to 0, then the absolute value is just x. Okay, understanding this expression here is really important. It says I'm defining a new procedure, the absolute value of x. Every time somebody calls abs on a number like -3, x will be bound to -3, and then I'll evaluate if -3 is less than 0, then negate -3, and I get 3. Question? Great question. No. So every if special form, you have to say what happens if it's true and what happens if it's false. Uh-huh. Yeah, so what does that alternative x mean? That's a good question. That says the value of abs x is just x if it were the case that that predicate was false. So if x is greater than or equal to 0, then abs x is just x. That's why it's just a plain x. Just a coincidence. I mean, in the sense that Excel stole it from lists. Ah, great question. Let's try it out. What if I say if 0, then 7? Otherwise, 8. Oh, 7. So 0 is a true value. In Scheme, the only thing that's false is false. Everything else is true. There's one other exception, but I haven't told you about it yet, so it'll have to wait. But there aren't as many things that are false in Lisp as there are in. Okay. So now you know a lot. You know how to define new procedures. You know how to say, you know how to do some control because you have if. And you can define new symbols. And what happens when we put all these things together? Well, we're just writing programs. And we're programming with exactly the same set of ideas that we had before. By the way, when you define abs, this creates a procedure and binds it to the symbol abs. Okay. So if I want to define the square function, what does that look like? Well, I multiply x times x, and that's how I square x. And what happens if I square 12? I get 144. Now, it's not the case that I have to put this in an interactive session. I can also put it in a file, just like I could in Python. So here's a regular file called x.scheme, and here I've defined what it means to square something. I'm also going to define what it means to average two numbers together, x and y. How do you average x and y together? Well, you have to add them together and then divide by 2. And that's how you average x and y. If I want to use the contents of this file, I have to load it. Now, loading something means writing the name of the file and a single quotation mark before it. You'll actually get used to this single quotation mark because we'll use it a lot, but just assume that it's magic for now. Okay. So it says okay, at which point I can average two numbers. What's the average of 3 and 7? Well, that would be 5. So we can square stuff, we can average stuff. What about something more complicated, like taking a square root? I never taught you how to take square roots yet, did I? Here's a way to take square roots. You guess some number for the square root of 256. Say, oh, I think it's 2. Now, your guess is wrong, because 2 times 2 is 4. That's not 256. So you update it with a better guess. And the update is called the Babylonian method. It's very old, from the Babylonians, 2,000-year-old method for taking square roots. The way you get a better guess is that you average your current guess and x divided by your current guess. So you average 2, and 256 divided by 2 is 128. If you add those together, you get 130. Divide that by 2. You get 65. 65 is actually a new guess. And you do this over and over again until you get the right answer. Really? Does that work? Let's try it. Okay, so I said, here's how you take the square root of a number using the Babylonian method. You have to come up with a way of improving your guess. You improve your current guess by taking the average of your current guess and x divided by your current guess. Close the average, close the define. Now, how do I do this over and over and over again? Well, I need iteration. I need like a while statement or a for statement or something, right? No, we can use recursion. So I'll define a recursive function that iteratively updates my guess until I get the right answer, called square root iter, which takes in a guess. It needs a base case. A base case happens when it's the case that your guess times itself is equal to the number that you're trying to take the square root of. I guess we can write this as the square of the guess is x. So if the square of the guess is x, then guess is definitely the square root of x. At which point, the value of the square root is just the guess that I came up with. Now, if that's not the case, I need a better guess. How do I get a better guess? Well, I call square root iter again recursively on an improved version of my guess. What does it mean to improve the guess? Well, you just average the guess with x divided by the guess. And what guess should we start out with? Well, how about 1? Okay. So I've written a recursive function inside of another function. I've used the name x inside this define, even though it's out here as a formal parameter of this define. And that's okay, because the same scoping rules that we used in Python also apply to scheme. At which point I can load this file, and if I'm lucky, taking the square root of 256 will give me 16. And if I take the square root of that, then I'll get 4. Well, we did something useful already. So I'm just combining the pieces of syntax that I've told you about so far. Now it does take some practice to get used to writing schemes. You're just going to have to sit there in lab and try some of these things out for yourself, and then soon enough you'll find that it becomes very natural to make sure that you have the right number of parentheses at the end that you opened up in the beginning. Okay, questions? Oh, why is this green? No, it's green because it's the thing that came after define. I could call it Rooty. I just want to make sure you believe me. Okay, now we can take the Rooty of 256 and we'll get 60. So we're not using the built-in square root in any way. We're just making guesses until we get the right answer. If I can do the square root of 255, let's try it. Oh my goodness, it's still running. So the problem is that there is no number that's exactly 255, the square root of 255 represented in the system that we're using. So we need to do something about that. And actually, if you ever came to the extra lecture series, there was a whole talk about why this works. But if you didn't come, then you don't know. Too bad. Although it is on video, extra lecture number 1. Okay. So, why are we learning this language again? Oh, it's important. It's full of foundational ideas. People still use it. It's beautiful. It's also there to prove to you that you already know how to program in multiple languages, not just Python. And it's there so that we can learn how it works. So the interpreter that I've been using to run all of the examples that you've seen today is actually just project 4 of this course. Your next assignment, aside from the homeworks, is to build a program that takes in a scheme program as input and outputs its value. And a program that interprets another program is called an interpreter. Now, how does it do it? Well, you just write down all the evaluation rules. How do frames work? How do call expressions work? How does if work? And then you're done. You run that program, and you've built yourself a programming language. That's cool. Okay. Python didn't invent the word lambda to be used for anonymous functions. That came from Lisp. Actually, it didn't. It came from the Lambda calculus. And the Lambda calculus was a written description of how programs should work that was later actually implemented as the Lisp language. So anyway, there's a long history. There was also an extra lecture about that, but if you didn't go, you don't know. Okay. So lambda expressions. What they do is they're expressions that evaluate to procedures. Those procedures don't necessarily have names. You just write lambda, and then the formal parameters in parentheses, and then the body of the procedure. Lambdas are important. There are two different equivalent ways to define a procedure that adds 4 to something. I can say define the +4 procedure, which takes in x and evaluates to x plus 4. Or I can say I want to define the symbol +4 to be the result of evaluating this expression, which evaluates to a procedure that takes in x and evaluates to x plus 4. When you write a call expression, you can put anything you want in the operator position as long as it evaluates to a procedure. So you could, in fact, put a whole lambda expression there. And it would look like this. Wow, so we have 2 different open parentheses at the beginning. That means I'm starting a call expression where I have to evaluate this expression to figure out what I'm calling. Okay, I'm calling a procedure that takes x, y, and z and adds x and y in the square of z together. That's the procedure I'm calling, and I'm calling it on x is 1, y is 2, z is 3. So 1 plus 2 plus 3 squared is 9, gives me a total of 12. So the first thing that happens is I have to evaluate the operator to figure out what procedure I'm calling, then evaluate the operands to figure out what arguments I'm calling them on, and then I apply the procedure to the arguments in order to get the value of 12. That's the same story as we had when evaluating a Python call expression. It's just the parentheses are now in a different place. You sure? Going once? Going twice? Okay. You now know about functions. I don't have anything else to tell you. But I haven't told you yet about data. So remember, we spent weeks on functions, and we spent weeks on data. Now we've spent 34 minutes on functions, and we're going to spend another 9 minutes on data, and then you'll know the whole language. Okay, so in Scheme, instead of having dictionaries and lists and sets and pairs and tuples, there's just pairs and lists. Unfortunately, they all have really confusing names, because in the late 1950s, when this language was invented, computer scientists enjoyed confusing people. And so, you have to memorize the following names. If you want to make a pair of two values, the procedure to do it is called cons. So if I say cons of 1 and 2, then I get the pair containing 1 and 2. If I want to get back the 1, the procedure is called car. That returns the first element of a pair. And naturally, since car returns the first element, the second element is returned by kdr, the procedure that returns the second element of a pair. If you want to refer to the empty list, which is a special value, it's called nil. Okay, so the idea of putting two values together into a pair should be familiar. Now you just have to know that it's not called a pair, it's called a cons, and it has a car and a kdr instead of a first and a second, or a first and a rest. Let's look at some examples of how to write down a linked list using a bunch of pairs. So remember, a linked list is a first element and then the rest of the list. So it's a pair. And pairs are fundamental to Python, to Scheme, in that they're used to build up linked lists, and that's how we represent sequences. So a linked list in Scheme is a pair in which the second element is either nil or another Scheme list. Here's the weird part, the confusing part. Scheme lists are just written in parentheses separated by spaces. And then there's this thing called a dotted list that has a value for the second element of the last pair that might not be a list. What? Let's look at some examples. Okay, so if I take cons, which makes a pair, and I cons together 1 and 2, that gives me the pair 1 and 2. And if I look at x now, it's written as 1.2. That dot means that I've created a pair where the second element is not a list. The car of that is 1, the kdr of that is 2. However, if I cons 1, cons 2, cons 3, cons 4, nil, what does this do? Well, this creates a pair where the first element is 4 and the second element is an empty list. So that's like a list containing 4. And if I have 3 followed by that list, that's a list containing 3 and 4, etc., a list containing 2, 3, 4, a list containing 1, 2, 3, 4. The way you write down a linked list containing 1, 2, 3, and 4 is with no dots, just parentheses, and 1, 2, 3, 4. So what I'm telling you is that when you see this output, parenthesis, 1, 2, 3, 4, close parenthesis, you're actually looking at a nested structure. That's a 1 as the first element, the car, and 2, 3, 4 as the second element, the cdr of the list. Whenever there's a dot, that means this is not a list at all, it's just a number. There's probably someone in the room who's confused because, like I said, they use confusing names and they use confusing notation. So let's play around with some examples and then you can ask some questions. Okay, so if I cons 1 and 2, I get 1.2. If I cons 2 and 3, I get 2.3. If I cons 2 and nil, I get a list containing 2, because nil is the empty list. So if I have the list containing 2, and I cons onto the front of that the number 1, now I have a pair where the first element is 1, and the rest is a list containing 2. So that's actually a linked list containing 1 and 2. So what do you think is the car of this? 1. And what do you think is the cdr of it? The cdr is the second element. That's the list containing 2. The cdr of the cdr is the empty list. All sequences are represented in this way in Scheme, so we got to just get used to it. Is there a question in the back? Every list is just a pair where the first element of the pair is the first thing in the list and the second element is the rest of the list. So no, it's not possible to have a list that's not a pair, because every list is a pair. So the question is, what happens when you cons together 1 with the cons of 2 and 3, I think? You get 1, 2.3. What's the car of that? 1. What's the cdr of that? Oh, that's the pair 2, 3. And the pair 2, 3 is just made up of 2 and 3. So there's only ever one dot, and that dot says the thing after the dot is not a list, it's just a number or something else. Yeah, cons always takes in 2 arguments, the car and the cdr. If you want to build a list and you're tired of typing cons 1, cons 2, cons 3, nil, there is a faster way. There's a built-in procedure called list where you can type in 1, 2, 3. What's the cdr of this? Tell the person next to you. Even though I created it with the list procedure, it's a pair. It's a pair of 1 and then 2, 3. So the cdr is the list 2, 3. This thing is always just a linked list. There is an origin to the name car and cdr, but I'll let you look it up. I'll let you look it up because it's a long story and boring. Okay. Here's another brilliant idea that Lisp introduced to the world. It's called symbolic programming. Normally, symbols just refer to values, like, oh, x is 2 and y is 3. But what if it were the case that we could refer to the symbols themselves? So if I define A as 1 and I define B as 2, and then I say list A and B, I'll get a list containing 1 and 2, because it'll look up A, it'll find it's 1. It'll look up B, it'll find it's 2, and I get 1, 2. But what if I wanted to put A, the symbol, into that list? There is a way. And it's called symbolic programming. And the feature of the language that we use is called quotation. you can refer to a symbol directly by putting a single quotation mark before it. So if I say list, quote A, quote B, what I get is a list containing the symbol A and the symbol B. Now, it might be that A is bound to something, or maybe not. But we're just talking about A, the symbol. It's like if you put scare quotes around something, not because you think it's scary, but because you actually want to talk about a word. So if you're writing an essay and you want to talk about, the word car, or coulder, and its origin, you would put the word coulder in quotes to refer not to what coulder is referring to, but to refer to the word itself. And we're doing the same thing here. We're putting a quotation mark in front of the symbol in order to say that we're talking about the symbol itself, not the value to which it refers. What happens if I list quote A space B? I get a list with the symbol A and the value for B, which is currently 2. So here, symbols are values. You can talk about the names of things just like you can talk about the things themselves. By the way, and here's where it gets pretty hairy, quotation can be applied to whole combinations. And what you get is a list. So I can say, quote, parentheses, A, B, C, end parentheses, and that quotation mark is applying to the entire combination, A, B, C, and this quote, A, B, C, evaluates to the list containing A, B, and C, which has the car A. And what's the coulder? The list BC. Yeah. The question is, what about strings? There are strings in Scheme, but we will never speak of them in this course. Instead, we'll only use symbols. So strings are only special because they can have spaces in them. Symbols can't. But you can always just have a bunch of symbols, and that's kind of like a bunch of words. Oh, so how do you get the value of the symbol? If you have the symbol, how would you get its value? Well, there's a built-in procedure called eval that evaluates the symbol, gives you its value. You want to try it? Define pi to be 3.141592653. That's enough. What's pi? Well, it's just pi. Well, what if I evaluated pi? Well, then I get the same thing as if I typed in pi. What if I defined x to be pi? What's x? Oh, it's just pi. What if I evaluate x? Well, then I get the number pi. I'm going to do a terrible thing to you. I'm going to show you a bunch of complicated examples in the last 2 minutes of lecture. But these they can just marinate in your mind. I strongly recommend that you understand this slide. I don't know if you can do it in the next 2 minutes, but let's go through it anyway. So, we saw that dots separate the list from the last element when the last element is not a list. And dots can be used in quoted lists as well to specify the second element of the final pair. So I could say, what's the coulder of the coulder of 1, 2.3? And we did this example before. The answer is 3. Now, when you write this down, the dot only appears when you don't have a well-formed list. A well-formed list is one where the second element is either a list or nil. So if I say 1, 2.3, that's the pair with 1 followed by the pair 2, 3. And that is not a well-formed list because this is not a list and it's not nil. So you see 1, 2.3. But, and here's the cool thing, if I say 1, 2 dot, and I say the thing that's the last element of this pair is the list 3, 4, then that's saying I'm going to create the structure 1, where the rest is 2, where the rest is the list 3, 4, and that's a well-formed list. So when you display it, even though you put a dot in the input, it'll just be displayed as a well-formed list 1, 2, 3, 4 in the output. Awesome. What happens if I quote 1, 2, 3 dot nil? Well, dot nil, nil is a well-formed list, meaning that I've built this structure, which means it's going to be printed out as 1, 2, 3. And if you want something to ponder as you walk to your next class, try to figure out what the coulter of this expression is. I'll leave it up for a few minutes. We're done for the day, and I'll see you on Wednesday.